Welcome back, AP Statistics. We're going to start this last portion of Chapter 17 with a practice problem that will have us flex a little creativity. So the CDC reports that the mean weight of adult men in the United States is 190 pounds with a standard deviation of 59 pounds. Source: an elevator in our building has a weight limit of 10 persons or 2,500 pounds. Okay? What is the probability that if 10 men get on the elevator, they will overload its weight limit? So, one way that we can think about this that will allow us to use the sampling distribution model for the sample mean is to look at this 2,500 pound number and this 10-person limit and say if 10 men get on the elevator, they would overload the weight limit if the average weight is 250 pounds or greater. 2,500 divided by 10 is 250. So if the average weight of these men is less than 250, then we're good. If the average is 250 or greater, that's going to be a problem for our elevator. So let's check the conditions to make sure that we can use the sampling distribution model for the sample mean. The randomization condition will assume the 10 men getting on the elevator are a random sample from the population. We're assuming here that a bunch of linemen are not getting in the elevator. These are just random men getting in the elevator. 10% condition. 10 men is surely less than 10% of the population of all possible elevator riders. Not just people in the building, people who ride the elevator. That's a very large number. So 10% condition is surely satisfied. Large enough sample condition. I suspect, and this is a reasonable suspicion, the distribution of weights in the population is roughly unimodal and symmetric. So my sample of 10 men seems large enough. Now, 10 is not really a good number for this unless you're assuming that the population is normally distributed. And with anatomical measurements like weight, that is a safe assumption to make. So we are able to use the normal model. And here's how we would do it. We want to find the odds that these men overload the weight limit. The average weight would need to be 250 pounds or greater to overload the weight limit. So we would say normal CDF, lower extremity is 250, arbitrarily high number, mean is 190, and the standard deviation is the standard deviation of the population divided by the square root of the sample size. Remember, this is the sampling distribution model for the sample mean that we're talking about. Since the sample mean is our random variable, it has the same mean as the population, but a different standard deviation, notably a smaller one. Take the population standard deviation divided by the square root of 10, and we get a very, very small number. So this 10 persons or 2,500 pound limit is good because if we get 10 people on there, the odds that we overload our elevator is very, 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 very small. So now we're going to get into part of the lesson that I told you about a little bit ago. I said we were going to cross this bridge when we got to it. Well, we are at the bridge. The central limit theorem with very skewed populations, okay? So recall that when sampling from skewed populations, we need a large sample size, a large enough sample size to justify using the central limit theorem. And that is the theorem that allows us to use the sample mean as a random variable. So to the left is a highly skewed set of data about the salaries of CEOs of Fortune 500 companies. This is straight out of your textbook. And to the right is a simulated sampling distribution of the means of 1,000 samples of size 10. All right, so how do we get from these data over here to this distribution over here? Well, what we did is we sampled 1,000 samples from this set of data over here. Each of those samples had a size of 10. Now, we want sample sizes of 30 and up, generally, and here's why. This distribution is not bell-shaped. Does that mean the central limit theorem is broken? No. The central limit theorem says that the sample mean as a random variable assumes a bell-shaped distribution given a large enough sample size. As sample size increases, the bell shape is more and more assumed. Sample size of 10 is too small. So let's see how big of a sample size we would need to make the central limit theorem work for us. So we're going to use samples of size 50, that's quite good, 100, that's awesome, and 200, wow, that's really good. So here is our samples of size 50. Here's 1,000 samples of size 50 from the population, and that's not really great, but it's definitely better than before. Now we're talking. We have samples of size 100, 1,000 such samples, and the mean is really looking normally distributed at this point with slight skewness. And by the time we get to samples of size 200, the central limit theorem is really working for us. The sample mean as a random variable is all but perfectly assuming a bell-shaped distribution. So let's talk about a potential misunderstanding about the central limit theorem. There's an old cartoon called Goofus and Gallant. Goofus does the wrong thing and Gallant does the right thing. And that is what Gary Cleveland Myers tried to convey in this informative and often rather silly and silly comic strip. The central limit theorem doesn't say that large enough samples drawn from any population are normally distributed. If we're just drawing samples from the population, they're not going to be normally distributed necessarily. The larger the sample you draw from the population, the more your sample will resemble the population, not necessarily a normal model. So if you're drawing from a normally distributed population, and it's a big sample, ideally randomly selected from the population, you're going to get a normal distribution for your sample. However, if you're sampling from a left skew population, you're going to get a left skew sample, okay? The central limit theorem says that the means of large enough samples drawn from any population are normally distributed. If you draw many large samples from any population and find the mean of each of those samples, the distribution of the means of those large samples fit a normal, a normal model. So now let's apply the central limit theorem and make sure we really understand it. And what better topic than human gestation? Human gestation times have a mean of about 266 days with a standard deviation of about 10 days. If we record the gestation times of a sample of 100 women, do we know that a histogram of the times will be well modeled by a normal model? Okay? Think about that. Think about your answer. Pause the video and unpause when you have an answer. Okay, let's see what the answer is. No, we do not. We don't have enough information to determine the distribution of the variable human gestation. Let's read this carefully. Human gestation times have a mean of 266 days, standard deviation of 10 days. If we record gestation times for the sample of 100 women, so we're sampling 100 women, good sample size, from the population, we're definitely sampling less than 10% of the population. Do we know a histogram of those times? We're not talking about sample means, we're talking about our sample will be well modeled by a normal model. We don't, all right? Now, since this is a matter of Since gestation is a matter of human biology, usually it is safe to assume a bell-shaped distribution. However, we don't know for certain, all right? So we're not going to make that assumption quite yet. Let's look at number 5. Suppose we look at the average, italics, that's an important word, average gestation times for a sample of 100 women. If we imagined all the possible random samples of 100 women, we could take and look at the histogram of all the sample means. What shape would it have? So now we're talking about a sampling distribution of sample means. How is the sample mean distributed? Well, that is going to be unimodal and symmetric. The central limit theorem says so, especially because we are sampling 100 women. That's way bigger than 30, and there is no evidence that we have that the distribution for gestation is significantly skewed. So we'll assume unimodal and symmetric unless we have a good reason not to think so. So where would the center of that histogram, that is the histogram for number 5, be? Well, where is the sampling distribution of sample means centered? Well, it would be centered at 266 days. Where does that number come from? That is the population mean. The sampling distribution of sample means has the same mean as the population. What would the standard deviation of that histogram be? Now that is the one that's a little challenging to remember. It's the standard deviation of the population, 10 days, divided by the square root of the sample size, which is 100. Square root of 100 is 10, therefore we have 1 day. Again, I'll say it again, note that the standard deviation for the sampling distribution of sample means is smaller and sometimes significantly smaller than the standard deviation of the population. A good fact to keep in mind. What you should also keep in mind is that you have homework, and there is a lot of hints on this homework, so please have your coursework sheet on hand or this slide on hand. Definitely want to refer to these hints for this challenging problem set.